Hello everyone, Assalamualaikum warahmatullahi wabarakatuh and good day to every one of you. Welcome to my video. So basically this is a continuation of a lecture video on chapter of induction machines. Okay, so my name is Dr. Nur Zulaili binti Muhammad. Here is my email address. So you can just feel free to email me whenever you have a question regarding the content of this video. Okay, alright, so basically in this video we are going to continue our lesson on the subtopics on equivalent circuit model for the induction machine. Okay, so let's move to the main topics of this video, which is equivalent circuit model for the induction machines. Okay, so basically the induction motor consists of two magnetically connected systems, which is stator and rotor. So if you still remember, in the topics on the constructional feature of the induction machine, you have a stator part, which is the static part, and then you also have a rotor part, which is the moving part of the induction machines. Okay, so this is basically similar to the transformer, where it also has a two magnetically connected systems, where for the transformer we call as a primary winding and secondary windings. Okay. And then in the induction machines, the stator part is actually supplied by the balanced three-phase voltage. And then from the voltage, it will drive a three-phase current through the stator winding. Okay. And then the three-phase current in the stator winding will be then induce a voltage in the rotor. Okay. So this is basically the basic principle operation of the induction machine that you had learned in the previous video. Alright. Okay, so this is actually the equivalent circuit model for the induction motor. Okay, so where here is your stator circuit, okay, and then this is your rotor circuit. Okay, so the stator circuit and the rotor circuit is actually connected by the magnetic coupling here. Okay, so basically the equivalent circuit model for the induction machine is similar to the transformer equivalent circuit. Okay, so if you still remember, this is the equivalent circuit for the transformer. The only difference between the induction motor equivalent circuit versus the transformer equivalent circuit is just the secondary winding, which is the rotor winding for the induction machine, is shorted at the end side, but for the transformer, it will be connected to any load. Okay, so that is the only difference between the equivalent circuit of the induction machine versus the equivalent circuit of the transformer. So based on the equivalent circuit model of the induction machines, we can actually find the V1 by applying the KVL at the first loop. Okay, so basically the applied voltage V1 across the phase A is actually equal to the sum of the induced voltage of E1 plus the voltage drop across the stator leakage reactance plus the voltage drop across the stator resistance R1. Okay, so basically the equation of V1 will be equal to E1 plus the voltage drop across the stator resistance is given by I1 R1 plus the voltage drop across the stator leakage reactance, which is I1 multiplied with JX1. Okay, so this is actually we can consider as the equation number 1, or we can also call it as a voltage stator equation. Alright, and then the induced voltage of E1 that produced in the stator winding will generate the voltage E2 in the rotor through the magnetic coupling. Okay, so the relationship between the E1 and E2 is different for the condition if the rotor is at standstill or if the rotor is actually moving. Okay, if the rotor is at standstill, meaning that the rotor does not move, okay, so the equation is given by E1 divided by E2 equal to N1 divided by N2 equal to A, where the A represents the transformation ratio. Okay, so basically the equation is just similar to the transformer. Okay, alright, but however, if the rotor is rotating, okay, the voltage induced in the rotor E2 is basically need to multiply by the slip S. Okay, because you know when the rotor is rotating, there is a difference between the NR versus NS, meaning that there is a difference between the speed of the rotor versus the speed of the stator. Okay, so there will be the value of S. So that's why the E2 now will be considered as E2 is equal to S multiplied with E1 divided by A. Okay, so from here, if the rotor is a standstill, so E2 is equal to E1 divided by A. But if you have the condition when the rotor is rotating, so you need to multiply this equation with S, with the slip, okay, where the slip is equal to Ns minus Nr divided by Ns, okay. So meaning that the stator speed minus, or we can also call it as the synchronous speed minus the rotor speed divided by the synchronous speed, okay. Okay, so again, based on the equivalent circuit model of the induction motor, so if the rotor is not moving, meaning that the rotor is a standstill, the relationship between the induced voltage is given by this equation, okay, where the E1 divided by E2 is equal to N1 divided by N2 equal to I2 divided by I1, okay, I2 is the current induced in the rotor, I1 is the current induced in the stator, is equal to the A is the transformation ratio, okay, alright. So the rotor induced E2 essentially can be calculated based on the applying KVL at the second loop. Okay, so E2 basically is equal to the sum of the voltage drop across the rotor resistance, which is the voltage drop is here is the I2R2 plus the voltage drop across the leakage inductance, where the voltage drop here is equal to I2 multiplied with JX2. Okay, so that's why here, if you apply the KVL, you will get this equation where your E2 is equal to I2 multiplied with R2 plus JSX2. Okay, alright. So once you apply the KVL across the second loop, and then next, from the previous slide, you know that from the equation 2, the relationship between the E1 and E2 is given by E1 is equal to A divided by S E2. Okay, and then you also, and then after that, you can just substitute this equation into here. Okay, so you can just substitute the value of E2 here. So E1 will be equal to A divided by S multiplied with I2 multiplied with R2 plus JSX2. Okay, alright. And then next, based on this equation, you know that the I2 will be equal to A multiplied with I1, right? Okay, so and then after that, we can just substitute the value of I2 here with AI1. Okay, so from here, you just substitute the value of I2 with I1. So that's why here you get E1 will be equal to A divided by S multiplied with AI1 multiplied with R2 plus JSX2. Okay, so we can actually rearrange the equation so that you have E1 will be equal to I1 multiplied with, so in this case you have A divided by S multiplied with A R2. So here you have A squared divided by S R2 plus A divided by S multiplied with A multiplied with SX2. So S and S will be cancelled out. So that's why here you have J A squared X2. Okay. And then after that, we can rewrite our equation so that we have E1 equal to I1 R2 prime divided by S plus JX2 prime, where the R2 prime is actually equal to the A squared R2. Okay, so here R2 prime is equal to A squared R2 and X2 prime is actually equal to A squared X2. Okay, so both R2 prime and X2 prime is actually considered as the rotor resistance and rotor reactance that refer to the stator side. Okay. Okay, so based on the derivation process that we had done in the previous slides, we will have the following equations, where the equation number 1, this is considered as the voltage stator equation. V1 will be equal to E1 plus I1R multiplied with R1 plus JX1. Okay, and then next we have equation 3, where E1 will be equal to I1 multiplied with R2 prime divided by S plus JX2 prime. Okay, so the R2 prime is actually the rotor resistance that refer to the stator side, and then this is the rotor reactance that refer to the stator side. Okay, so based on these two equations, we can actually substitute the equation number 3 to the equation number 1. And then we can get here E1, I will substitute with equation 3. So I can rewrite it as a V1 will be equal to I1 multiplied with R2 prime divided by S plus JX2 prime. So this is the E1 plus I1 multiplied with R1 plus JX1. Okay, and then after that we can rearrange the equation so that you have V1 equal to I1. Okay, so the R2 prime divided by S plus the R1. Okay, plus the imaginary part, which is JX2 prime plus JX1. Alright. Okay, so basically this is what we call as an induction motor equation. Okay. Okay, so again, the induction motor equation is given by this equation, just like in the previous slide. Okay, so based on the equation, we notice that it suggests that the equivalent circuit model contains of two resistance and two reactance that connected in series. Okay, so here you have two resistance and also you have two reactance that connected in series. Okay, so that's why based on the equation, you can draw the equivalent circuit model equal to the voltage drop across the R1 plus R2 prime divided by S and voltage drop across the JX1 plus the JX2 prime. Okay, alright. So the magnetizing current can be represented by the resistance RC and also reactance XM that connected in parallel. So basically the resistance RC represent the hysteresis and also represent the eddy current loss. And then the reactance here represent the magnetizing current that generates the air gap magnetizing flux. Okay. Okay, so I think that's all for now. We had learned on how to derive the equivalent circuit model for the induction motor. And then in the next video, we are going to learn on how to determine the parameter of the equivalent circuit model. So we are going to learn on how to predict the value of R1, GX1, the JX2 prime, and also the R2 prime. Okay, includes RC and also the XM. Okay, so I thank you for your time. Thank you for watching my video. I'll see you in my next video. Okay, bye.